Good day, ladies and gentlemen. Today we are going to discuss the Copula production function. Right. This is an overview of the session, and these are the details things that we'll be doing. We'll be treating this Copula function into details. Recall that we talked about a production function, various characteristics of this production function, and if you take the Copula production function, it's a specific production function. And what we will be doing is that we would be looking at all the what we discussed under the theory of the firm, and then knowing that the Copula production function is a specific production function, we will try to investigate how the function behaves. Now the literature is the same. Now this Copula function is of the form that we see over here, where k and L are raised to the power alpha and beta, respectively. We believe that alpha and beta are fractions. A is greater than 0, so V is the quantity of physical output, and all the other sort of variable are as defined over here. What we would like to know first is the marginal product. So we will try to look at the marginal product of the Copula function with respect to one of the input, let's say L. So when we take the marginal sort of the first derivative with respect to L, we get this, okay, which we can simplify as this. But notice that what we have standing here is the same as the function here, okay? So what it means that instead of having this one, we can put in the same function, right? So the marginal product of capital is obtained by just multiplying the function by alpha and divide by k. So if you want to know this function, the marginal product with respect to k, you just look at, multiply the same function by alpha and k, and then you are fine. Similarly, we can have the marginal product of labor, right, which can be given as we have over here, the same function, and then b multiplied by L. You can convince yourself by differentiating this function with respect to L and doing the usual substitution that we have done over here. Now, the second order derivative. So we know these are the first order derivative. This is the first order derivative with respect to k. So we can go further and take the second order derivative, and when we simplify, we get this. And again, you see that we can substitute what we have over here with a v, and then we have these equations, okay? So the second order derivatives gives us this value, or the value that we have over here. Now the negative means that the law of the diminishing returns is satisfied by what? The Copula function. Analogically, you can do that for the cross partials, okay? And I'd like you to take your time and then take the cross partials. We are going to get this, right? This, and then when you simplify, in place of this one, you put the same function, and then you have that. Now, what is the nature of the Copula function? It means, is it a concave function or is it a convex function? To be able to do that, as you know, we have to form, it's a function on two variables. You recall that we discussed concavity and convexity using the Hessian determinant. So it means here too, we have to use the Hessian determinant. Earlier, we have found the first, second order, partial derivatives, and also the cross partials, which that is what we've done up to date. So you just insert, so this is the first order cross partials, partial derivative with respect to k, with respect to L. These are the cross partials. So when we insert them into the Hessian determinant and then we simplify, we get a function of this nature, okay? We can factorize this out, and then we also simplify it, and we get an equation of this nature. So the question is that, will this value be greater than 0, less than 0, or equal to 0? And it's from here that you'll be able to know whether the function is concave convex, or strictly concave, or strictly convex. Now, these are the conditions under which you are going to get a Copula function to be concave, or a Copula function to be what? Convex. So once you are able to determine, right, the value of alpha and the value of beta, it will always I'll help you to know the concavity or the convexity of the function once this equation has been, determined. Now, what is the nature of the isoquant? You would like to know whether the isoquant again is concave or convex. So we have a function here. We said isoquant is the combination of input that yields a specific level of output. So if we assume that our output VO is K, it's constant, that is VO over here, then we can express K in terms of what? L. When we take the first order, derivative, we get this, and when we take the second order derivative, we get this. And if we have these conditions, that alpha being a fraction, L being greater than 0, then we have this one being greater than 0. So this equation becomes, greater than 0, and then we know the nature of that, isoquant. Analogically, we can do it for L, and then we have this one, and then we have, so what it means is that for a Copula function, we can have the isoquants to be what? Convex, and that permits us to use it very well in many analyses. Now, the elasticity of substitution, which we talked about, this is a formula for elasticity of substitution, which we discussed last week, right? And in that equation, we had F1, F2, but here we are changing with V1, VL, VK, just for comfort, right? So this is our function. If we change the K to X1 and then the X2 to L, we have this function. And if we take it that these are the differentials of the Copula function, and then we insert them into our elasticity of substitution function, which is here, right? We insert all the first order, the second order into the function, the values are here, and then we evaluate, we get 1, right? So what it means is that for a Copula function, the elasticity of substitution is equal to 1. I would like you to go through this activity, take this function, we call the function constant elasticity of substitution, and then try to, investigate the function, the first order, the second order, and then find the elasticity of substitution of this function we have over here, which is a specific, Copula function. So here the alpha and the beta has been given, and you need to play with this function. Having discussed the, this Copula function, what I would like us to know now is to discuss the optimizing behavior of a firm, okay? In a neoclassical firm, the firm technically solves, 5 sort of problems. The first one is output maximization, which you may have come across. We have, cost minimization. We also have profit maximization, and these are all more or less unconstrained optimization. We have output minimization subject to a fixed sort of cost, and so also do we have cost minimization based on a specific production quota. So in all these discussions, you may need to know whether you are going to use constrained or unconstrained optimization to solve these problems. And here I provide one example here where a certain company has got this function, and we are supposed to find a level of output that maximizes the firm's profit. So it's a straightforward function. As usual, we go through that first order differentials. We talk about our Hessian determinant, we evaluate them, the principal diagonals, and then we get our maximum to be what we have over here. So what I'm trying to do is that once we now know our Hessian and our bordered Hessian, we have to apply them to 5 sort of problems that any neoclassical firm, faces once we know the nature of the production function, that it satisfies the basic conditions of a production function, then we can do some maximization. So the example over here is also here constraint optimization, which as usual, and here it's applied to a specific firm, and then you can know how to, discuss that. So you can take your time and go through this solution, and I have some activities here for you. Now, what have we done in this section? Some activities here, very nice questions that you can solve. If you have problems, we are going to meet at the chat room and we will discuss it. So try and be at the chat room. There's also another question here, right? These are very nice questions talking about the new classical behavior optimization problem of a firm. Thank you very much.